All right. Good morning, everyone. Thank you for coming this morning. I'm William Lambert. I'm from Virginia Tech over in the States. And I'm going to be presenting on leveraging OpenFOAM for hydrodynamic parameter computations of near-surface underwater vehicles. So just underwater vehicles, small AUVs that are close to the free surface, but not yet piercing the free surface. So as a quick overview of what I'll be talking about today, in case there's some other talk that you want to go and this isn't exactly what you thought it was, I'm going to be talking about some novel hydrodynamic parameter computations, particularly using OpenFOAM. I'm going to talk about parameter-based motion modeling, some of the applications of using parameter-based motion, and also how we get those parameters. Traditionally, we use virtual planar motion mechanism testing, but today I'm going to talk about how I implemented an impulsive motion model and energy-inspired estimation techniques. I'll go through some of the validation of those motions, the robustness of them, and some of the next steps following. How do we use those to inform motion models, and in particular, energy-based motion models? So this work was conducted under the Virginia Tech iShip team at Virginia Tech. And we have strong collaborations with the Virginia Tech Center for Marine Autonomy and Robotics. The Virginia Tech iShip group is advised under Dr. Stefano Brizzolera. We do a lot of different work, ranging from propeller design, supercavitating hydrofoils, AUV stepped planing holes, novel ship design. And the Center for Marine Autonomy and Robotics works on all sorts of autonomous vehicles, mainly underwater vehicles for seafloor mapping, but there are also some surface vehicles and auto mooring devices that we have. So kind of an introduction into hydrodynamic motion modeling. It can be used for a variety of different applications, ranging from path planning, coming up with conceivable paths that underwater vehicles can take. They can also be used to inform control design. In particular, we are looking at using it for energy-based control algorithms. We looked at motion prediction and maneuvering feasibility and safety testing. So instead of always having to run full-scale CFD, we can put a vehicle, if we have its hydrodynamic parameters, to see if it's a feasible vehicle and whether it's going to be safe in waves for a particular motion. Typically, we use virtual planar motion mechanism testing, which is deriving the vehicle parameters using oscillatory motions. One such motion model is one for underwater vehicles that are close to the free surface, shown at the bottom, where we have several hydrodynamic parameters, such as the added mass or the damping. And one particular important one is the convolution kernel for memory effects. And this is able to predict underwater vehicle motions underneath waves, which is shown in this video, where a body starts off orthogonal to some incoming waves, and slowly the near surface body gets pushed off its path. So this was one example of a lumped parameter model where we use a variety of different parameters that are then lumped together to calculate the motion dynamics. It uses a combination of unsteady and steady CFD to capture some important effects, such as propeller hole and rudder hole interactions. It is using long-term oscillatory motions to derive these parameters. And there's some problems that come along with that. One is that it's frequency and amplitude dependent. So whatever frequency that we use to derive these hydrodynamic parameters, such as the added mass, there is a frequency dependence on that, which we can show for that same underwater vehicle shown on the right. We see a peak and a trough for the added mass, ranging with depth dependent on the frequency of oscillation used. It also involves long simulation times. We want to reach steady state, and then we want to run several periods of motion for these oscillatory motions. So we are looking towards these impulse-like simulations to get the same sort of parameters. And this was kind of inspired by Cummins' integral equation, which is shown at the bottom, but adapted for near surface vehicles. And we see that the hydrodynamic forces depend on an infinite frequency added mass, the added mass associated with impulsive motion, and a convolution term that accounts for the motion history, the memory forces of the body, which is the convolution, how the forces evolve with time from that impulsive motion. And looking at the hydrodynamic parameters in this way, it allows us to separate the impulsive and the memory effects from one single motion. It also allows us to look at the analysis of energy propagation through time. If we run an impulsive motion and then immediately stop the body, we can see how that energy convolves with time. So the impulsive motions that we implemented inside of OpenFOAM is a ramped acceleration from rest. So we don't immediately start the body. We use a ramped acceleration over a very short amount of time, 1/1000th of a second initially, so that we don't have any of these force spikes, these pressure spikes inside of the simulation. We're starting from rest and we smoothly accelerate to a given acceleration. We then use least squares fitting to model the hydrodynamics using a couple of different damping models. One, over such a short amount of time, we wanted to know, is damping even relevant? And then we also have a linear damping model and a quadratic damping model. The plot on the bottom right just shows the results of this least squares fitting using a linear damping model. And we see that the least squares force estimation matches the actual force output from the simulation very well. So in order to run these simulations, we use the Naval Hydro Pack using Naval foam. This was great because it uses volume of fluid with the ghost fluid method and isoid vector systems to get a sharp interface, even when the free surface is not perturbed all that much. To simulate the short impulsive motion, we use 6-degree freedom domain motion. So we don't have to mess around with overset meshes. The entire domain moves. To model viscous modeling, we've used two different kinds. We have a completely inviscid model to as closely match potential flow analysis as we can, so we have zero viscosity in the fluid. We use a laminar boundary condition and a moving slip boundary condition on the body. For the viscous modeling, we of course have normal water viscosity. Because it is such small velocities around the body for this short impulsive motion, we use a laminar turbulence model. And of course, a moving wall boundary condition. The entire simulation is second order in time and space. These are an example of the near surface body where we refine the free surface to capture those small perturbations on the free surface. We also have a boundary layer around the body for y plus less than 1. So what we actually did, we wanted to first check the feasibility of using an impulse-like model for the prediction of added mass. Starting from added mass, slowly we'll add on damping and the convolution term. So we look at mesh and time step sensitivity first, and then look at acceleration independence. Can we use different accelerations for this impulsive model? We also look at timescale effects. Like I said before, initially we started with time steps of 1/1000th of a second. We wanted to see, does that capture what we want it to? Do we need smaller time scales, or do we need larger time scales to actually capture what we want? We also look at near surface proximity. How do these added mass parameters change with respect to depth and proximity to the free surface? And even looking at some coupled motions. Are we breaking any linearity assumptions? Are the motions coupled with each other? And then I go through a brief analysis of energy-based terms. Using these impulsive motions, can we derive a Lagrangian system, the kinetic energy minus the potential energy within the system? So first, we look at the mesh convergence for a deeply submerged body. On the left, we see that as cell count increases, we approach the analytical formulation for added mass. I show sway. It works for all relevant degrees of freedom for a submerged spheroid. So there's 5 degrees of freedom. Roll doesn't really matter. And then on the right, we show the square 2 norm from the least squares fitting. And from that square 2 norm, we see that the linear damping model for both viscous and inviscid flows has the lowest error. I show the same thing for shallow submergence. So when the body is located very close to the free surface, a submergence of 0.75 diameter is measured from the central body axis. And we see the same results. We see the monotonic convergence with respect to the mesh. We also see that the linear damping model performs best across the range of meshes that we used. One important thing to note, however, is that the added mass is decreased from that analytical formulation. We also look at the time step used for these simulations, ranging from 2 times 10 to the -5 all the way down. And we see there isn't as large of an effect with respect to the time step used, but there is an effect as we decrease the time step, we get closer to that analytical formulation. And again, the smaller the time steps used, the more accurate the simulations, especially with respect to the linear damping model. These clues are all adding up that we still need a linear damping model to model the flow around the body. Looking at the shallow convergence, again, there's not that much change with respect to the time step. But we still see that the linear damping model works well and that the added mass is decreased for the shallow submergence case. So now we come to acceleration independence. Can we use different accelerations and still get the same added mass value despite of the acceleration used? So we used 3 different acceleration ramps shown on the right with their respective velocity curves. We had acceleration amplitudes of 25, 5, and 1 meter per second squared over this small time scale. And we see the plot on the right using the linear damping model for both deeply and shallowly submerged in both viscous and inviscid simulations, which actually coincide on top of each other. That there is no difference with respect to the acceleration amplitude used. So this impulsive motion model is independent of the acceleration used. Then looking at the time scale, so the effect of how long this acceleration is applied to the body. We use 5 different time scales to understand the effect that running longer simulations has on the body. And we see both those time scale ramps and the results on the right. We see, I used surge in this case instead of sway because of the length in the body compared to the diameter. And we see that the inviscid cases don't really have an effect with the timescale used. However, once we add in these viscous effects, we see those results begin to diverge as we get longer and longer timescales. A reasoning behind this is the creation of a boundary layer around the body. There's this gradual growth of a boundary layer. If we allow more time for that boundary layer to grow, we're not assuming any sort of already existing boundary layer. So there needs to be some time for that boundary layer to grow. This creates a change in the effective size of the body. With the velocities scaled to the maximum velocity of that particular ramp length, we see that the ramp length of 0.05 seconds compared to 1/1000th of a second is much larger. We see this growth of the boundary layer, which changes the effective size of the body, which when a body accelerates, you're then accelerating more fluid around the body, which increases the added mass. And then I'll actually go back. And so if we move backwards in smaller and smaller time steps, the inviscid and viscous cases actually converge on one another. So viscous effects aren't actually all that important at such small time scales. This will lead into some future studies when we're running from steady state with an already formed boundary layer. We then move into some depth effects. So how do these added masses change with respect to depth? Are we able to capture depth effects. And we can see that as depth increases, as the depth to the diameter ratio increases, that we approach the analytical formulation given by Lamb. But as we get closer to the free surface, we see a dramatic decrease in the added mass of the body. This is caused by an asymmetry in the fluid domain. We have, in a deeply submerged case, we're surrounded by a much more dense fluid. However, when we're close to the free surface, you're then accelerating air, which is a lot less dense, requires a lot less force, which in turn decreases the added mass around the body. This is shown by the dynamic pressure around the body, where we see an asymmetry for the near surface case. It squishes the dynamic pressure on top of the body, whereas in the deeply submerged case, we see the dynamic pressure encapsulating the body. We see this asymmetry physically caused by the free surface and the change in density across the free surface. Looking at some coupled motions, understanding that if we can combine two motions, we can capture actually a couple of different added masses instead of just running a pure linear acceleration in surge or in sway. So we couple surge and sway, and then in a separate simulation, sway and yaw. So we have translation, and a translation and rotation motion. And these are plotted with respect to as if a single motion was used. And we see that there is no noticeable difference in running a coupled motion versus each motion individually. So we are able to decouple these simulations. If we have the added mass and surge, we can simulate and model a coupled motion using the individual degrees of freedom. Moving into the energy part of the presentation, the energy-inspired parameter estimation. The main inspiration, the goal of this is to develop a Lagrangian nonlinear maneuvering and sea-keeping model, which is derived from first principles using energy considerations instead of force considerations. So we look at the parameter estimations using boundary element methods initially. This, of course, makes some drastic assumptions on the fluid, including potential flow and a linear free surface boundary condition, which in some previous papers of mine showed that making that linear free surface boundary condition is no good. So we're moving towards a physically realizable model using OpenFOAM to derive these energy terms used in the Lagrangian model. So instead of using potential functions, we want to use the velocities and the free surface elevations of a simulation to derive the kinetic energy and the potential energy of the system. And this will give us a better understanding of the energy convolution. So the Lagrangian system developed by a previous student at Virginia Tech is given at the bottom, where the top line really involves the kinetic energy of the system. It looks very similar to 1/2 mv squared, which we know from physics. The bottom line deals with the convolution of how that energy is transferred to the free surface in terms of a free surface memory effects convolution integral, seeing how the interplay between kinetic energy and potential energy is. So using Naval foam, we run a simulation. We can either get the added mass from looking at the output forces, which is normally done even with BPMM, or we can write an internal function for the simulation to calculate the total kinetic energy throughout the system, which is actually very easy from rest. You can just sum up all of the velocities within each cell across the entire domain. And then using the assumption that the kinetic energy is 1/2 added mass times the velocity of the body squared, we can then arrive at the added mass from a different direction using the energy of the system instead of the forces on the body. So first we have to check that assumption that the kinetic energy is accurately modeled by 1/2 MAV squared. And it is. We can see that the kinetic energy versus 1/2 body velocity squared on the left shows a very good linear regression. Looking at the added mass outputs on the right, we see that there is a difference between calculating the added mass using the forces and the kinetic energy, but it is very small. For the case of surge, which has throughout the study shown the greatest difference in the added masses, is still less than 3%, 3.3% different, and is even less than 1% for the other degrees of freedom. This difference is mainly caused by, for forces, you're only integrating the pressure around the body, where you already have a very fine mesh. But if these velocities travel away from the body, you have a less fine mesh, those errors start to add up a little bit by little bit. So you would need a more fine mesh around the body to capture the kinetic energies. But vice versa, we wouldn't necessarily need to use the kinetic energies to calculate the added mass for this Lagrangian model. But we just want to show that we can model the kinetic energy using the added mass derived through other methods, whether that be analytical or boundary element methods or BPMN. We can still calculate the kinetic energy. So this study was focused on the use of short impulsive motions compared to oscillatory motions to predict hydrodynamic parameters. Some of the possible benefits of using this impulsive motion model include quicker simulation times. We're only running 1/1000th of a second compared to several frequency oscillation periods. It's also frequency independent. We're not depending on the frequency of oscillation, having to run several different simulation oscillation frequencies, but instead we can use Cummins' integral equation and just use the infinite frequency added mass. We also start to see the separation of impulsive and memory effects. We don't have the boundary layer, but we could impulsively stop this body and see how the energy evolves with time, separating that impulsive acceleration and then what happens after it. Some possible drawbacks, of course, include those time-dependent effects. If there are shed vortices, or if there's interaction with past flow. And so that leads into some of the future studies that are ongoing now, is running these impulsive accelerations from a steady state, whether that be straightforward motion or a motion with a constant pitch or drift. We're also looking at the parametric estimation, how we did with kinetic energy, but the same thing for the potential energy. So is there a parameter that we can use to model the potential energy of the free surface deformations? And then, of course, all of this would culminate in the application to a Lagrangian system for motion modeling. Thank you. Yeah. I need to look back at that. It's fairly close. Yeah. 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 So since these accelerations were at such small scale, you reach very small velocities around the body. When we move to the steady state cases, we plan to do for fully turbulent modeling. But I believe there is a possibility in that for sure. I have done some reduced order modeling, but mainly for the free surface elevation, not necessarily looking at the added mass, but there's that possibility. Thank you.
Okay, just to reintroduce myself to the online participants, my name is Marko Horvat. I'm joining you from Wiki Limited in London, and I will be talking about the interesting study I did recently on propeller. It was actually a propeller of a surface combatant, and I was using multiple reference frame, and everything was nicely compared to model tests. So yes, let's just jump into it. This is the ship that this propeller was actually attached for. The ship was studied during one of the previous NASA conferences. For more information, you can click on the link at the bottom, and you will be presented with a lot of information about the ship, what particular cases did they study, what were the results, and so on. But just to give you an order of magnitude and reference, you can see that this was a model scale case of around 3 meters in length, with a wetted surface of around 1.5 meters squared, and the propeller diameter is around 100 millimeters. And all the experimental data are publicly available. So if you want to redo the test, you are more than welcome to, and you have access to all the resources. When it comes to the propeller and the meshing, this was probably the most painful task in this study, because I did everything in pointwise, everything manually, and it took me a couple of days to do that. But in the end, we have a quite good mesh with which is fully structured. It has 25 million cells, which is probably an overkill for this diameter of the propeller. But what we wanted to do is to keep our Y plus very well under 1. So we can see that our maximum Y plus is at an order of 0.1. So we are not using any wall functions. We wanted to test the low Reynolds approach. And the mesh quality is quite good. It's the maximum orthogonality below 70 and max skewness at around 1.7. And you can see some snapshots of the mesh and how does this look. When it comes to the domain and how I set up the boundary conditions, this is pretty much the summary. I split the domain into 2 subdomains, one dealing with the propeller, the other dealing with the far field, and they were connected with general grid interfaces. The boundary conditions are quite standard, so I prescribed the fixed velocity at the inlet, and I fixed the pressure at the outlet. And I've been using K omega SST as a turbulence model. The propeller spins quite fast for ships. It's 10 revolutions per second, but it's a model case, so yes, this is expected. And as I said, I've been using multiple reference frame to model rotation. When it comes to the processing of the results, this will be basically repeating in the later section. What I've been doing is I've recently found that this method where you just take a look at the wake, you draw this type of circles on it, and you just pick up some points in it, and then you see how your variable, how your metric is behaving with the angle, and you are getting quite nice curves, which are which you can then repeat for any other metric that you want. Here, the sampling is quite coarse, so this is why you get this ugly picture, which is not symmetric. It doesn't repeat. But in this, here I used, I don't know, 20 sampling points just to give you an example. But in the next examples, I will be showing you much more dense, much denser sampling, and the graphs will look much prettier. And also for the next couple of slides, I'll be focusing on the results which came out of the simulation with advanced coefficient equal to 1. And I will be showing you later a comparison between this one and different advanced ratios as well. So this is how the story looks for the axial velocity. So I repeated the same post-processing technique on the right, and you are basically able to see how the velocity changes in this radial direction at the different radii. So this is showing you for 30, 50, 70, 90, and 110% of the radius of the propeller, and you can see how the velocity develops. So basically, if you start from 30% of the radius, you're somewhere in the middle with quite significant oscillation. And then as you increase with the radius, you get higher velocities, which is quite expected. But then as you're approaching the tip of the blades, the velocity actually starts dropping and you're getting less oscillation. And then at 110% of the radius, you get something that looks like a sinusoidal curve there. And you can see that this all repeats 4 times as you go around the circle, which is quite expected. You have 4 blades in the end. When it comes to the y velocity, this is probably not the best metric to check here, but it gives you some sense of what happens with this direction. I'm saying that this is not probably the most representative, because you would get the same story if you checked the z component of the velocity, and you see here that it's not repeating 4 times if you're going around the circle, but it actually repeats twice, with the fact that it's mirrored around your x-axis when you cross the 180 degrees, and we basically mirror it over the x-axis and then push it to the 180 angle to just get the full angle. But you're also able to see how it develops by increasing the radius. So if you start from 30, 50, and 70, you are pretty much in this band over here. Yes, but then as you go higher with the radius, you are actually getting more peaks and something more interesting. And of course, when you go out of the diameter of the propeller at 110% of the radius, you get something that is pretty much around 0, which is kind of expected from the image on the left. When it comes to this cross section, I'm plotting here the magnitude of velocity and a couple of interesting points here. First of all, you're getting the stagnation point where you expect it, just at the front part of the hub. And you're getting the maximum velocities at the tip blades, and also these maximum velocities kind of repeat in space as you go downwind to the propeller. You're also getting some interesting features and structures just where the hub is connecting to the shaft, and I will be showing you this in more detail later with a couple of Q isocontours just to see what the coherent structures are expected there. When it comes to probably the most important part in this study, the pressure distribution on the blades, because we were really interested in the moments and forces. You get pretty much what is expected. I limited the range here a bit just to see something, because if you just put it at the full range, you cannot see anything, because this highest pressure is just very concentrated on the blade tips, and yes, everything else will look green. So yeah. When it comes to the pressure, this is how the pressure field looks like in the wake. And again, the same post-processing. You start from the 15% of radius here. I started here because you actually have some values here for the velocity. It was just 0. So yes, you start with very, very negative values, and then as you increase your radius, you go to the positive values, and then probably the most interesting part is at the 90% of radius, where your circle just goes through different regions of very low pressure and very high pressure. So you get this big oscillation of the pressure at that radius. Yes, and these regions of the very low pressure are basically that. So your tip vortex is just propagating through these regions into your domain in the axial direction. And also some other expected coherent structures. So you're getting this horseshoe-like vortices at the tip of the blade, where the blade meets the hub, and also a couple of interesting structures just at where the hub is attaching to the shaft. Okay, and probably the most important graph of this whole study. So we tested how good are we compared to the experimental results for different advanced coefficients, and you can see that our coefficients of thrust, torque, and the efficiency of the simulations quite good, especially for the lower advanced ratio coefficients. Everything works nicely until the last point, and I don't really know what happened there. I am not able to find anything wrong in my simulation, so I don't know. Probably it will require some more investigation on my part, or just say that results are the experiments are wrong, which I don't really want. But yes, and this is where I would like to finish the presentation. Thank you. Yes, please. That's a bit a tricky question. I don't really know, but I assume that it would change a lot. Yeah. Yes, so this is, if I go back, maybe it's the best to show it here. It's 0.02 meters behind the blades. So basically what happens, I was checking many different locations of it. And basically what you get with this post-process, you're just getting the graph shifted in the direction, because this is all repeating itself, just swirling around the axial axis. So basically what you would get, okay, not exactly, because there are some changes in the axial direction, but what you would get is just this image, this screenshot just rotated around the axial axis. So this is why I think this post-processing technique is quite nice for this type of things. There is some, yeah, there is something, especially when I was looking at the Q isocontour with this vortices, they dissipate quite quickly when you leave the MRF zone into the static zone. Yes, but because I'm expecting that this is because there is a jump of 2 to 3 in the volume of the cells when doing, because this is already a very big mesh, and I was not really able to afford many more in the far field. Okay. Thank you very much.
To talk about the numerical models that we developed in red for dynamics to characterize the performance of the surfboards. Surfing is a very ancient sport. The first historical evidence is from 1778 by the discoverer of the Hawaiian Islands, James Cook. But despite this very ancient age, the shapers, despite to the contrary of what happened in many other sports, such as, for example, the America's Cup, the shapers doesn't follow a scientific approach to develop the new surfboards, but they based their new designs just on their own intuitions and on the feedback of the pro surfers. And as you can see here in this example, one of them is trying to demonstrate the functionality of this tool installed on the tail of the surfboard, just spraying the water on the bottom of the surfboard. And so, as you can easily understand, there is nothing scientific on this kind of approach. So, starting from this point, and for sure, pushed by our passion for surfing, indeed, Brad, we are all surfers. From the 2016, we start to develop several models, OpenFOAM based, to characterize the performance of the surfboards and of the fins. The reason behind OpenFOAM is that, as you observed in the previous slide, is that the surfing factory doesn't invest a lot of money in research and development. And so OpenFOAM is the best tool to do this work. And in the next slides, particularly, I talk you about the models that we use to simulate the surfboards. Basically, we have two different models, the static one and the dynamic one. In both the models, the surfboard is placed in a domain in a water tank-like setup, where it's invested by a multi-phase flow treated with the WOF technique. And the runs equation are solved, and the K-omega SST model is employed. To reach accurate enough results, we use always second-order numerical schemes. Talking specifically by the models, the static one uses the pseudo-transient approach to resolve the equation in time, and due to the the static position of the board and the steady boundary conditions. The dynamic one, to the contrary, employed the transient approach with the Euler first-order schemes, and to simulate the movements of the surfboards, the overset technique is mandatory because the very wide movements performed by the surfboards. And for sure, we have to define manually the movements to be assigned to the surfboards. The models, particularly the static one, are fully automated on the Italian HPC platform, Cineca, with a very simple ORAN script where in the first part, there are all the inputs. And then starting from the inputs selected by the user, the geometry is selected from a warehouse folder where we store all the geometries, is set in the domain, the mesh is built with the utilities of OpenFOAM block mesh and SnappyX mesh, and then the simulation is performed. More attention is required to the generation of the mesh that is, as I said, fully automated, starting from the generation of the background grid that is characterized by a vertical gradient from the upper and lower patches to the interface between the fluids. Then a series of horizontal refinement is performed in order to reach an isotropic resolution in the volume around the surfboard. That is required first to have a good quality of the mesh in the area where the gradients are placed, and also to reach a good coverage of layer on the surface of the board. That is quite challenging with the SnappyX mesh. At the end of the process, an extra refinement is performed at the interface between the fluids, excluding from this refinement the cells around the surfboards in order to preserve the quality of the mesh, as you can see in the picture in the right corner. Just the blue cells are refined and the green one not. During the development of the model, we encountered several numerical challenges. The first was the layer coverage, as I said, but now thanks to the new algorithms implemented in Snappy, we are now able to extrude more or less 95% of the layers. Then the other challenges are the numerical ventilation and the stability of the dynamic model. Talking specifically of the numerical ventilation, this is an issue related to the VOV technique that occur when simulating planning bodies characterized by small angles between the planning surface and the interface between the fluids, such in this case. We try a lot of recipes to resolve this problem, like for example, changing the resolution of the mesh, increase the resolution of the interface, change the schemes and something else. But at the end, the only way to resolve this problem is use the interface compression boundary condition on the surface of the surfboard that works applying just a binary value to alpha water, 1 when the computed value is higher than 0.5, and 0 when the computed value is lower than 0.5. So it is a very crude way to resolve the problem, but it is the only one for this specific setup of the board. As you can see here, a comparison between the zero gradient boundary condition and the interface compression boundary condition. The maps with the interface compression boundary condition are for sure more realistic and more clean, particularly alpha water and the shear stress. To better understand the potential of the model, here we have a very simple example. We have three different designs characterized by the same outline, but by a different rocker. The rocker is the displacement of the extreme parts of the shape from the lower one. And so we have the neutral shape, that is the standard rocker one, and then the flat tail rocker and the flat nose rocker, characterized by a lower tail rocker and a lower nose rocker. The board are placed in the so-called cruise setup, so the boards are traveling straight in the water. And looking at the results, you can see how small differences in terms of geometrical parameters can lead to very huge differences in terms of performance of the board. Particularly change the tail rocker, we have a very similar drag, but a 200% more lift. So it is important to do just small arrangements to the geometry to reach the desired results. As I said, it was the most simple example from our simulation. We can do also more complex analysis. For example, here we are simulating a full maneuver of the surfboard, but it is not just a random maneuver. This is the reproduction of a realistic maneuver performed by a surfer. And with this model, we are able to monitor the forces during the full maneuver and do, again, comparison between different designs, and so help the shapers to reach the desired goal. So to conclude, we have now the static model that is fully working, fully automated, and is able to simulate the surfboard in any kind of position. The dynamic model requires a bit of development because the stability is not has to be improved. And for sure, also from the point of view of the code, the overset is not exactly suitable because of the computational cost associated particularly to the interpolation of the results from the background grid, so the static grid, to the moving grid. And so it has been to improve a little bit to be more suitable for this application and for sure for other many applications. Thanks for your attention. We could simulate the waves, but at this stage, the important thing is characterize the performance, and the wave does not affect the performance of the board. Yeah.
Could you maybe take a look at measure the board with something else that let's say that some of your style, like assembly already done, you know, so that's there. So
yeah, we try with CF mesh, but the problem with CF mesh is that it doesn't allow to reach the desired resolution on the wall. Snappy is most suitable from this point of view, and for sure is not very simple to manage to reach a good quality of the mesh. But just CF mesh, any other code for meshing.
for the last presentation, this is going to be a bit different because the presenter is not with us here in person, so he sent us a pre-recorded presentation. The presenter's name is Sanijo Đurasević, joining us from University of Zagreb. I believe that he is online with us, so the questions will be able to be asked by you, and he will join us online to try to answer them. And he will be talking about SHIP-PROPELLER interaction analysis with the hybrid partially rotating grid method. So let me just find the presentation and start it. But Sanijo, give us a shout if you are with us so that we know if the questions can be asked and answered in the end. Okay, we can maybe try again later. Do they just need to unmute themselves to communicate with us, or? Okay, so only through the chat. Okay, Sanijo is with us in chat. Okay, we will do it then in this way. We will ask Sanijo questions here, and he can answer in the chat. Okay.
Hello everyone, my name is Sanijo Đurasević. I'm a PhD student at the Faculty of Mechanical Engineering and Naval Architecture of the University of Zagreb. Today I'm going to present you our recently conducted research involving ship-propeller interaction analysis with newly introduced partially rotating grid method. So let's start. New regulations regarding energy efficiency of new ships and of existing ships introduced by the International Maritime Organization increased demand for CFD in now hydrodynamics. Application of CFD ranges from predicting self-propulsion coefficients necessary for power estimation and propeller design to a more detailed analysis of the transient phenomena induced by propeller rotation. Experimental measurements are, so to say, gold standard, but their complexity and large costs pose limitations. Also due to different flow conditions and the Reynolds number in model and full-scale, application of extrapolation procedures is questionable for some purposes. The main goal of this study is to be able to reduce overall computational time while still achieving accurate numerical prediction of the self-propulsion test, which requires adequate representation of the propeller. Fully discretized rotating propeller and variety of body force-based methods are most commonly used nowadays to model the propeller. Fully discretized propeller represents the most accurate approach, but the limitation of this method is that the simulation time step needs to be really small in order to capture the flow phenomena and near the propeller. In order to try to mitigate this limitation, we introduced partially rotating grid method. The idea behind the partially rotating grid method is to combine the fully discretized rotating propeller approach that actually moves the grid in space with a locally introduced non-inertial system. Angular velocity vector can be expressed as the sum of the angular velocity of the rotating appendage grid and angular velocity vector of the non-inertial system, which enables derivation of the momentum equation in a relative frame of reference with absolute velocity in a form as presented in a slide. In this equation, omega r cross product u is a source term which represents Coriolis force contribution, which is added only to the rotating appendage region. As the convection term consists of both relative and absolute velocity, phase volume flux correction is applied to be able to solve the equation using absolute velocity. Also, velocity values of the moving boundaries inside the rotating appendage region are updated, taking into account contributions from relative and inertial frame through boundary condition. A study in this research is performed for a well-known cruiser container ship with a KP505 propeller. Ship particulars for both model and full scale are presented in the table. This container ship geometry is chosen due to publicly available experimental data for both local and integral flow characteristics. Simulations are performed on both model and full scale geometries. Both hull and the propeller in this study are assumed hydraulically smooth. To assess the validity of the introduced method, a set of propeller open water simulations is performed for 3 different propeller rotation representations. First one, noted with uppercase A, represents non-inertial method where the appendage grid is kept constant, stationary during the simulation. Case B represents partially rotating grid method, which takes into account both inertial and non-inertial contribution. And case C represents purely inertial propeller method. Simulations are performed for the full-scale propeller, and the results are compared to the corrected experimental data. Experimental data which are available for the model scale propeller are scaled using statistical scaling method specified in 1978 ITTC performance prediction method. Expected self-propulsion point is near J 0.7, therefore relative differences between experimental and simulation data presented in the table are calculated for this specific advanced coefficient. Over-prediction to under-prediction trend of torque coefficient value is visible when the inertial frame contribution is increased, while thrust coefficient is under-predicted for all cases. Also, open water efficiency is under-predicted for every case. By observing the obtained results, conclusion can be derived that the ratio of contributions from the inertial and non-inertial propeller rotation representations does not affect the integral values of open water characteristics significantly. Especially in case of lower J values, if the figure on the left side is observed, which is actually expected given the uniform inflow conditions. Overall, good agreement between the computational and correct experimental data is obtained, which shows that the introduced method is capable to predict accurate integral values. To estimate the practical engineering feasibility of these computations, non-dimensional computation times with respect to the non-dimensional contributions from the non-inertial propeller rotation representation are presented in figure on the right side of the slide. Non-dimensional computation time is calculated as the ratio of computation time of the current case and the computation time of the fully transient computation. It can be observed that contribution from the non-inertial propeller rotation representation allows a larger time step to be used. As a consequence, overall computational time is reduced. As the double body model approach is employed to perform self-propulsion simulations later on in the study, bare hull resistance simulations with and without free surface are performed in order to estimate wave-making resistance component. Wave-making resistance force is estimated from the wave-making resistance coefficient using the expression presented in the slide. Also, accurate prediction of the bare hull resistance force is important to conduct valid self-propulsion simulations due to the fact that the propeller rotation rate is controlled based on the value of the longitudinal force acting on the ship. If obtained results in the table are observed, it's visible that with the larger Reynolds number achieved in full scale, frictional resistance component is less dominant in total resistance. Overall good agreement with the experimental value of total resistance is achieved, satisfying the condition for conducting self-propulsion simulations with sufficient accuracy. Accurate capturing of the free surface is also important to determine wave-making resistance force, which is necessary for the self-propulsion computations using a double body model approach. Overall good agreement with experimental data is obtained if the wave elevation is observed. Difference in boundary layer thicknesses affects wave elevation, specifically downstream of a stern, which can be observed in the figures. Viscous effects are less pronounced upstream of the stern area, so the difference in wave elevation between model and full scale is smaller. These observations imply that the wave-making resistance is Reynolds number dependent. Here, the non-dimensional velocity contours sampled in the propeller plane are shown. Non-dimensional velocity values are larger in full scale due to different boundary layer thicknesses. Smaller average velocity in model scale means a larger value of wave fraction, which has a direct impact on the propeller load. Self-propulsion simulations are performed in both model and full scale, with symmetry plane boundary condition to represent the free surface. Simulations in model scale are performed taking into account difference between model and full-scale frictional resistance. Rotation rate representing non-inertial component is kept constant during the simulation, while inertial rotation rate is controlled using a PI controller, where controller set point is chosen to be desired resultant force in the longitudinal direction. In case of model scale simulations, this force is equal to difference between skin friction correction and wave-maker resistance forces. While in case of full scale, it's equal to the negative value of the wave-making resistance force, because the skin friction correction force is equal to 0. In this slide is presented discretized domain with boundary condition, which is used to perform self-propulsion simulations. Simulations are performed for two different propeller rotation representations, namely partial, denoted with letter A, and inertial, which is denoted with letter B. In case of partial representation, approximately 90% of the contribution is from the non-inertial frame, and the rest is from the inertial frame. Now, here are presented integral values or results obtained from the simulations, and model scale values are compared to the publicly available experimental data. Model scale computations generally underpredict torque coefficient, thrust coefficient, while overpredicting torque coefficient. This implies that possible erroneous assumptions in estimating wave-making resistance are employed. Thrust deduction factor and wake fraction are in good agreement with the experimental data, while propulsive efficiency is underpredicted mainly due to underprediction of open water efficiency, which is also observed in case of propeller open water simulations. Difference between model and full-scale thrust and torque coefficient are mainly due to different flow distribution at the propeller plane and average inflow velocity. Due to larger effective wake, internal boundary layer propulsive efficiency is larger when compared to model scale. From the obtained results, it can be concluded that the propeller is operating in more efficient conditions in full scale, which can also be concluded if the curves of thrust and torque coefficient ratio is observed. This ratio has a similar meaning as lift to drag ratio. It describes propeller blade performance in terms of efficiency. A larger average value of this ratio can be observed in case of full scale, which, as mentioned before, implies better efficiency in full scale. Ratio decreases and reaches its minimum at approximately 210 degrees in case of partial propeller rotation representation, and at approximately 250 degrees in case of inertial propeller representation. Minimum occurs in a tangential position where usually values of the inflow axial velocity are lowest and the angles of attack are larger. The difference in thrust over torque ratio curves between cases A and B are mainly present due to the effect of the propeller rotation representation on the flow field upstream of the propeller plane. Smaller differences between minimum and maximum values of KT or KQ in full scale are due to more uniform inflow conditions when compared to model scale. In this slide, first thing to notice is that asymmetry and moon crescent-like region are captured in model and full scale for both partial and inertial propeller rotation representation. As expected, inertial propeller rotation model captured the non-dimensional velocity contours more accurately when compared to the experimental data, than the partial propeller rotation model. Due to different propeller load and wake in front of the propeller, position of the high velocity region is different for every case. Position of high velocity region moves counterclockwise in case of partial rotation representation. Contours of the low velocity region, which are located behind the hub, follow the same pattern. This behavior may affect the pressure distribution downside of the propeller plane, which may be significant if the rudder is present. Also, it's visible that the high velocity region is largely full scale. If experimental data are observed, it's visible that cross-flow vector field consists of a dominant main vortex and smaller counter-rotating vortex located in the upper right part of the propeller disc. Inertial propeller rotation model captured the position of the smaller vortex more accurately. Location of the smaller vortex is shifted counterclockwise in case of partial rotation representation in both model and full scale. And finally, it can be concluded that the partially rotating grid method introduced in this research offers accurate prediction of integral flow characteristics while being able to reduce computational time. The accuracy of the method is dependent on the ratio of inertial and non-inertial propeller rotation contributions. Although the predicted integral flow quantities are less sensitive to this ratio, the accuracy of local flow phenomena is more affected. Differences in boundary layer thicknesses and Reynolds numbers between model and full-scale conditions have notable impacts on propeller inflow conditions, load, and performance. For more information about this method and to see more detailed analysis of the results, I kindly refer you, if you're interested, to the recently published paper, Partially Rotating Grid Method for Self-Propulsion Calculations with a Double Body Ship Model. Or feel free to contact me privately for more information. So, at the end, I want to thank you all for your attention. I hope you have a great time in Genoa, and that's it from me. If you have any questions, please feel free to ask.
Hello, hello, can you hear us? Yeah. The online participants were unable to hear the presentation. Can you hear us now? Sanya, if you could just write something in the chat. Okay, perfect. Great, thank you very much, Sanya. Very, very nice talk. Just a quick question from my side. I remember during yesterday's keynote talk by Professor Jacek, he showed one of your simulation results with the zigzag motion of that ship, which was very, very impressive. And I've noticed that the propeller was rotating quite slowly there. Is this the same method that you were presenting today? And if so, how do you decide what the rotation speed of the propeller is? The audience, if you have questions, sit down without the mics so that Sanya can hear. Okay, so I hope that you can see. Are you able to see that? So Sanya says, yes, this is the same method, but just first implementation and testing under single-phase solver. But in nature, it's the same logic. And how do we come up with the rotation speed? Because So I noticed that the propeller was rotating slower than you would expect for the ship of this size. And I think that Professor Jacek also mentioned that the propeller is rotating slower. So could you comment on that, and how do you decide how fast your propeller should be spinning? It's very likely possible that I misunderstood something. So you can just. Okay, I see. I see. Okay. Okay, thank you very much. Any other questions from the audience? Does not seem so. So if not, yes, this is then the end of the session. Thank you very much for joining us. Thank you very much, Sanijo, and other presenters as well.